In this second video for Chapter 2, we're going to look at another type of first-order differential equation, differential equation called a linear differential equation. We looked at these in the first section. They are first-order differential equations that can be written in this form: dy dx plus p of xy equals q of x. Remember, the requirement for linearity was that neither the derivatives nor the variable of the differential equation were raised to a power. The other components of it, the p of x and the q of x, can be functions that are raised to powers. So how do we solve a differential equation of this type? Well, it turns out that we can actually develop a formula. So let's see how to develop that formula. Let's take the right-hand side of the differential equation and multiply it, or actually let's multiply first the entire differential equation through by mu of x. When we do that, here's what we get. And then what we're going to do is take that that left-hand side and set it equal to this. Set it equal to the derivative of the expression mu of x times y. So let's take a look at that on the next blackboard. So it's mu of x times dy dx plus mu of x times p of x is set equal to d dx of mu of xy. We're trying to find a mu of x that solves this dE, because then we'll be able to write the left-hand side of the differential equation like this, which is a much simpler way to write it, and it will lead to it having a solution, or to it to being very easy to solve. So let's first solve this differential equation. So the right-hand side of this differential equation, if we apply the product rule to that derivative, we get what? Mu of x y prime, or mu of x dy dx, plus mu prime of x times y, and that is set equal to what was already the left-hand side, mu of x dy dx plus mu of x p of x. Well, it turns out that there is a good amount of cancellation, right? This and this are the same, so they cancel out, and so we have the much simpler differential equation remaining: mu of x p of x equals mu prime of x y. Well, that turns out to be a separable differential equation, because the only occurrence of y is right here. So that's not, actually I had a little error here. There should be a y here, right? There's a y sitting here in our original equation. So that puts a y here and a y here, and there should be a prime right here. So let's go to the next blackboard and see what we have. So we have mu of x p of x equals mu prime of x. Not only is it separable, but there's only one variable left in it. Right, because the y's are going to cancel out on this left-hand side. Right, this y and this y cancel out. So we're left with this, which we want to rewrite to show that it really is a differential equation. Remember, there's a prime right here, so it's mu prime of x over mu of x equals p of x, and then we can just integrate both sides of that, and so that gives us then what? This is essentially a u over du, so it's ln of absolute value of mu of x, and then this side remains as the integral of p of x dx. We are going to leave off the plus c because, as it turns out, well, let's actually go forward a couple steps and see why we can do that. So we're going to make both sides powers of e. I'll put the plus c in here for now. And so the right-hand side becomes... Alright, so we got to the point that mu is this. And the mu of x does not need this constant c. Let's actually put it in blue, because if we go back here, if we put that constant c here, here, and here, here, and here, we can just divide through by it, and so it doesn't play any role. So let's go back to where we are and rewrite our mu of x without the constant c. Mu of x is our integrating factor, and so there we have it. Mu of x is that. Remember that our objective was to rewrite the left-hand side of the differential equation, this, as this, which we are able to do when we find the mu of x. So going back to our original differential equation, we're going to write the left-hand side of it now as d dx of mu of x y. So let's pick that up. So we've got what? D dx of mu of x y equals mu of x q of x. Right? That's our differential equation. Right? We replaced this with d dx, this left-hand side, all of this, with d dx of mu of x y, and that's equal to this right-hand side, which was mu of x q of x. So that turns out to be an easy differential equation to solve. D mu of x y equals mu of x q of x. Move the dx, multiply both sides by dx to get this. Then integrate both sides of the differential equation. And on the left-hand side, we just have the integral of the derivative, and so the integral and the derivative just undo each other, and on the left-hand side we just have mu of x y, and on the right-hand side we're left with an integral, mu of x q of x dx. So we've solved it for y when we divide through by mu of x. So we get now y equals 1 over mu of x integral of mu of x q of x dx, and that is the solution of a linear differential equation. A little bit hard to remember maybe, but only for a little while. It should become easy to recall after a few times of working through with it. When we do this integration step right here, we do need a plus c, and so let's be clear that we that plus c winds up here, right? We move it from the left-hand side over here to the right-hand side, and so it ends up right here. Okay, so let's do a couple applications of this linear technique of solving a differential equation. So can we take this differential equation here and turn it into the linear form? Well, yes, if we rewrite it like this, dy dx, we take this part right here, the y over x, and write it as plus minus 1 over x times y, and then leave the 2x plus 1 over here, and then we can see that we've identified the parts, right? So this, the minus 1 over x, is the p of x. Here's the necessary y on the left-hand side, and all of this right here is the q of x. Okay, so we should be able to just put everything into the formula. So mu of x, well, mu of x is, remember, e to the integral of p of x dx. And we said just a moment ago that our p of x equaled minus 1 over x, right? That's what we got right here. And so when we integrate this, we're going to get what? So it's e to the integral dx over x with a minus sign out front, which is e to the minus absolute ln x, which is e to the ln absolute x to the minus 1, which is just absolute x to the minus 1. So mu of x is this. So y equals 1 over mu of x, which is 1 over absolute x, bracket, integral, mu of x, 1 over absolute value of x, q of x, which was 2x plus 1, right? So 2x plus 1 and dx plus c. Well, this integral is a little bit cumbersome with the absolute value in it. Let's consider two cases. If x is greater than 0, then absolute value of x is just x. And so in that case, we just have y equals 1 over x is x. And under the integral sign, we just have x times 2x plus 1 plus c. Put the dx in here. And that gives us y equals x. When we are integrating this, we're integrating what? 2x squared plus x. And so we get what? X, or 2x cubed over 3 plus x squared over 2 plus c. So that's one solution. If if x is less than 0, then absolute value of x equals minus x, because that turns it into a negative. So let's write this alternate form of the solution as y equals minus x, and then it's minus x under the integral sign, so we're integrating just the negatives of what we had before. And we see that when we distribute this minus sign across, we get the same thing as before for most of it, x times 2x cubed over 3 plus x squared over 2, but it's then minus c here times x. So just a teeny difference here with the constant, and the question is, for a particular constant c, does it make a difference? In this case, it turns out to not make a difference, so we could have just done this one case of the solution as is typically true. Let's take a look at another example where it may not involve the absolute of x and be a little bit easier to get to a solution. Okay, so here's our second example. We need to put it into the correct form, which is dy dx plus p of xy equals q of x. So that would be what? We're going to divide through everything by x, so dy dx plus, and then we get 2 over xy equals, and this is still x to the minus 3. So our p of x is 2 over x, and our mu of x is e to the integral of that and so that is what, e to the 2 ln absolute x. That, if we bring it over here, is e to the ln x. We don't need the absolute value because it's squared, so already positive. So mu of x is just x squared. Right? And then the form of the solution is y equals 1 over mu of x integral of mu of x q of x dx plus c. So filling everything in, mu of x, remember, was x squared, and so 1 over mu of x is x to the minus 2 bracket integral x squared. The q of x was x to the minus 3 dx plus c. This becomes then what? X to the minus 2. Everything under here becomes what? Dx over x. So we get what? Times ln of absolute x plus c, and if we distribute that across, we get what? Ln of absolute x over x squared. Remember, we have to distribute that mu of x across both, so it's plus c over x squared, and that is equal to our solution y. Okay, that better. So how about dy dx plus 4y, so let's write that 4 times y equals e to the minus x. If we tag the things here, it's actually already in the right form. The p of x is just a constant, and the q of x is e to the minus x. So mu of x would be e to the integral of p of x dx, which would just be e to the 4x. So y equals the reciprocal of that, which just changes the power to negative integral e to the 4x e to the minus x dx plus c. And so what we are integrating here is e to the 3x. So we get y equals e to the minus 4x. We're integrating e to the 3x, which is e to the 3x over 3 plus c, and then we distribute the e to the minus 4x across and get e to the x, or e to the minus x over 3 plus c e to the minus 4x. And there we have our solution. So these linear differential equations, or differential first-order equations which are linear, are straightforward to do. Doesn't mean the integrals are always simple, and they can get a little bit complicated when we have two cases, if an absolute value turns out to have two cases. But a lot of cases don't have that complication, and this example 2 here and this example 3 are relatively easy. So this is going to conclude this second video from chapter 2 on linear differential equations, where the model comes from, and how to solve linear DEs using that model or formula that comes from the model.